The examples in this lesson go with section 5.1, Fundamental Trigonometric Identities. Example 1, simplify. Write the final form with no fractions. Cosine theta plus sine theta, cosine theta over sine theta plus sine theta over 1 plus the cosine of theta. Okay, we need to take these two fractions and turn it into an expression that has no fractions in it. Okay, well, if this were regular math and we had something like 1/3 that we were trying to add to 2/5, the first thing we would want to do is get a common denominator. And so that's exactly what I'm going to do. I'm going to multiply the numerator times this denominator. So we're going to have the cosine of theta times 1 plus the cosine of theta plus, and then I'm going to multiply this denominator times this numerator. That's going to give me a sine squared theta. And then in the denominator, my common denominator is just going to be those two multiplied together, the sine times 1 plus the cosine. All right, let's distribute this cosine into the parentheses here. That's going to give me the cosine squared of theta plus the cosine of theta. And I just put a square on there, and I should not have done that. Sorry. Let's try that again. Plus the sine squared of theta. All right, so all I did was cosine times 1, that gave me cosine theta. Cosine times cosine, that gave me cosine squared. And over here, we already did the sine times sine, that gave me the sine squared. In the denominator, we have the sine of theta times 1 plus the cosine of theta. All right, now we know from the Pythagorean identity that when I add the cosine squared to the sine squared, that's just going to simplify to 1. So the numerator turns into the cosine of theta plus 1, and the denominator still sine theta times 1 plus the cosine of theta. Well, that means our fraction can actually reduce, because I have a cosine theta plus 1 here and a cosine theta plus 1 here. Then we're left with 1 in the numerator and the sine of theta in the denominator. And I know that's still a fraction, but the sine is a reciprocal function, and it is a reciprocal function for the cosecant. And now we have simplified our expression. Example 2. Simplify and write the final form with no fractions. 1 minus the secant squared of t divided by the tangent of t minus the tangent of t times the secant of t. Okay, once again we have a fraction and we're trying to simplify this expression so that it has no fractions in it. Now, one thing I notice about the numerator is that I have a secant squared and I have a 1, so I can use my Pythagorean identities here. And I look down here in the denominator and I don't have anything squared, so the Pythagorean identity is not going to be very helpful here. So I'm going to try another method. The numerator up here will actually factor, and in the denominator I notice that both of my expressions have a tangent in it. That will factor as well. So what I'm going to do is I'm going to factor the numerator. It is a difference of squares, and it factors into 1 plus the secant of t times 1 minus the secant of t. And then in the denominator, I'm going to factor out that GCF, which is the tangent of t. And that's going to leave me with 1 minus, and when the tangent's gone, I'm just going to be left with the secant there. Okay, now my fraction will reduce because I have a 1 minus the secant in the numerator and in the denominator. So let's cancel these out. That's going to leave us with 1 plus the secant of t over the tangent of t. All right, so what I have now is I have a numerator that has 2 parts to it, and I have a denominator which is just 1 part here, and so I'm going to separate these into 2 fractions. I'm going to write this as 1 over the tangent plus the secant divided by the tangent. And already 1 over the tangent I know has a reciprocal function, that's the cotangent. So we can take the denominator out here by turning this into the cotangent. And this one, I think we're going to have to turn this into sines and cosines so that we can eliminate our fraction. So the secant, which is 1 over the cosine, and then the tangent, which is the sine over the cosine. And what I'm going to have to do is invert this bottom fraction and multiply. So let's come up here. We have the cotangent of t plus 1 over the cosine of t times the cosine of t over the sine of t. So we did the invert and multiply thing. And now it looks like I have 2 things that can cancel each other out. So the cosine and the cosine will cancel. That leaves us with the cotangent of t plus 1 over the sine of t, because 1 times 1 is 1, and 1 times the sine is going to give you the sine. And then the sine actually has a reciprocal function, which is the cosecant, so we can turn that into the cosecant, and now we have an expression that has no fractions in it. Example 3, verify that the equation is an identity. The sine of negative x times the cosine of negative x divided by the cosine of negative x is equal to 1. Okay, sorry, that's the sine times the cotangent. So we have the sine of negative x times the cotangent of negative x divided by the cosine of negative x is equal to positive 1. Okay, first thing, it's going to be a whole lot easier to take all of this over here and simplify it down into something than it is to take 1 and blow it up and try and turn it into something that looks like this. So when you're working with an identity, you're only allowed to work on one side, and you have to pick a side. And the only exception is when you get stuck, and then when you get stuck, you still have to go back and fill it in on the correct side so that it looks like you're only working on one side. But let's just go with the rule, you can only work on one side of an identity. Okay, you can't add and subtract stuff to each side. What we're trying to do is we're trying to take all this over here and simplify it down until I have the same thing over here that I have over here. Okay, all of these are taking the trig function for a negative angle. Okay, now the sine function we know is an odd function, which means that this negative I can just bring out in the front right here. That turns this expression into the negative sine of a positive x. The cotangent is also an odd function, so I can just bring its negative out in the front here. That turns this expression into the negative cotangent of a positive x. And then in the denominator, the cosine is an even function, and so we know that the cosine of a negative angle is the same thing as the cosine of a positive angle, so our denominator is going to simplify into the cosine of positive x. And then we're just going to keep our equals 1 here. Okay, in the numerator, a negative times a negative here is going to give me a positive. That leaves me with the sine of x times the cotangent of x divided by the cosine of x, and this is still equal to 1. Okay, now there's a couple of ways I can go about finishing this, and I think what I'm going to do is I'm going to separate this into a fraction, the sine divided by the cosine times the cotangent. This is one way I can do this, but it's not the only way that will work. And then this will be equal to 1. And the reason I did this is because this is actually a quotient identity. The sine of x divided by the cosine of x is the same thing as the tangent of x. And then this will be times the cotangent of x, and we're still equal to 1. All right, let's bring this up here. We have the tangent of x. The cotangent, I know, is a reciprocal identity. It is the same thing as 1 divided by the tangent. And this is still equal to 1. And now look at what we have. If I put a 1 underneath here, my tangents are going to cancel out. And I have 1 times 1 on the top, 1 times 1 on the bottom. I have 1 on the left side, and I wanted 1, and we're finished. Example 4, verify that the equation is an identity. 1 divided by 1 minus the sine of x minus 1 divided by 1 plus the sine of x is equal to 2 times the tangent of x times the secant of x. Okay, in a case like this, I'm probably going to choose the left-hand side here because it's easier to change an addition or addition or subtraction into a multiplication over here. So I'm going to be working on the left, and I'm going to try and make it look like what I've got going on the right here. Okay. Now, going back to what we did in example 1, I've got 2 fractions here. Let's get a common denominator. So I'm going to multiply this numerator times this denominator. That's going to give me 1 times 1 plus the sine of x. And then I'm going to multiply this denominator times this numerator. So we have minus 1 times 1 minus the sine of x. And that minus came from right here in the middle. And then the denominator is 1 minus the sine of x times 1 plus the sine of x. And we want all this to be equal to 2 times the tangent of x times the secant of x. Okay, let's multiply everything. We'll distribute the 1 into the parentheses. We'll distribute the negative 1 in the parentheses. And I'm going to go ahead and FOIL the denominator here and see what happens. All right, so 1 times 1 is 1. 1 times the sine, that's going to give me plus the sine of x. Negative 1 times 1 is going to give me negative 1. Negative 1 times the negative sign is going to give me a positive sine x. In the denominator, 1 times 1 is going to give me 1. 1 times the sine of x is going to give me a positive sine x. The negative sign times 1 is going to give me a negative sine x. And then a negative sign times a positive sign is going to give me a negative sine squared x. And this is all equal to 2 times the tangent of x times the secant of x. All right, let's simplify in the numerator and in the denominator. In the numerator, I can see that the 1's are going to cancel out because 1's positive and 1's negative. And then the sine plus the sine, that's going to give me 2 of those sines. In the denominator, I can see this positive sign and this negative sign are going to cancel. That's going to leave me with 1 minus the sine squared of x. And this is equal to 2 times the tangent of x times the secant of x. Okay, the denominator down here looks like a Pythagorean identity because it has a 1 in it and it has a sine squared. But our Pythagorean identity is adding things together, it's not subtracting. So let's take a look at it. Let's come up to the side over here. We know that the sine squared of theta plus the cosine squared of theta is equal to 1. And I want 1 minus the sine squared, so let's subtract the sine squared over here to this side. Then we're going to be left with, let's see, those sine squareds are going to cancel each other out. Okay. we're going to be left with a cosine squared here. And on the other side, we can't combine those. They're not like terms, so we have 1 minus the sine squared of theta. Now what this means for me is that I can actually substitute a cosine squared here for that 1 minus sine squared. And this all came from our Pythagorean identity. So let's do that. That turns my problem into 2 times the sine of x over the cosine squared of x. And we want this equal to 2 times the tangent of x times the secant of x. Okay, now I'm going to break apart this cosine squared, and I'm going to write this problem as 2 times the sine of x divided by the cosine of x times the cosine of x. And we want that to be equal to 2 times the tangent of x times the secant of x. All right, now I'm going to break this apart into 3 fractions. All right, one of my fractions is going to be 2, or 2 over 1. One of my fractions is going to be the sine divided by the cosine. So this is being multiplied by sine x over cosine x. And this is going to be multiplied by this cosine x right here, but remember there has to be a 1 on top of it because it is in the denominator of a fraction. And we want this to be equal to 2 times the tangent of x times the secant of x. Well, I wanted a 2. I've got my 2. The sine over the cosine, this is actually one of our quotient functions. The sine over the cosine is the same thing as the tangent. So we have 2 times the tangent of x. And then 1 over the cosine is a reciprocal identity. That goes with the secant. So we can turn that into the secant of x. And on the other side, we have 2 times the tangent of x times the secant of x. This is what I wanted, and so we have proven our identity.